Okay, so this chapter is called thermochemistry, and thermo usually gives us what indication that we're talking about what? Heat, right? Thermal or thermo are good indicators for us of heat. And so we're going to talk first about energy and a concept called work, okay? And then we're going to get into heat and some calculations for heat. But first, we're going to introduce energy a little bit. So energy is anything that has the capacity to do work or to produce heat. So if something contains energy, which everything does, it has the capacity or the ability to do work, okay? Or it has the ability or the possibility of producing heat. The law of conservation of energy is something that we have gone over before, and we indicated a lot by saying energy can be neither created or destroyed, right? You have heard that concept before. That's nothing new, and if you already have it in your notes, I don't think that's something you need to have down again. So as we walk through it today, you don't have to write everything down word for word, right? Please use an abbreviated version because this has a lot of stuff to go through. Okay, so law of conservation of energy tells us that every energy in the system or in the surroundings is conserved. And so we're going to look at a total conservation of energy within experiments, within reactions, with all this kind of stuff. Energy is not created nor destroyed. It's just switching forms, right? It could go from heat energy to light energy to whatever else, right? It could have lots of forms of energy, but it just changes form, okay? In order for that to be true, or another explanation of that is that the energy in the total universe, right, is just one value. There's X amount of joules of energy in the universe. Joules is the unit for energy. We'll go over that in a second. There's X amount of joules of energy. I don't know what that is. I don't know that anyone necessarily knows what that is. But there's X amount, right? And that amount does not get bigger or smaller. It just changes forms, right? It's like a pie, right? So different pieces of the pie will change sizes, right? But the pie itself doesn't get bigger or smaller. That's energy in the universe, okay? So, basics into energy. There's two types of energy. We're not going to talk a whole lot about those, so I just want you to hear me out a little bit, okay? You don't need to really know the difference between these two in terms of their definitions, okay? This is stuff that we'll look at in physics a little more intensely, but potential energy and kinetic energy are the two types of energy, the two main types, basically, okay? Does anyone know what the prefix kina usually means? Motion, right? Kinetics, kinematics, those are all motion. So kinetic energy is an energy an object in motion. Potential energy is the energy that an object has stored, right? What does it have the potential to do? That's what potential energy is stored energy. Kinetic energy is what energy it maintains while it's in motion. So objects can have both. They can have all one kind or all the other kind, right? Or they can have a combination in both. That's not something that we're going to look at a whole lot right now. It's just something to think about in terms of energy, okay? So with that, I'm going to show you a little picture here, and we're going to talk about potential and kinetic energy in two objects just so you can visualize it a little more carefully. But again, not something that you necessarily need to have written down. Okay? In our first drawing, we've got ball A, that's being held above ball B. Okay? Right now, A is at a position that it could fall and do work, right? Or apply a force and displace an object, and displace object B. Okay? So if it has potential energy, that means it's stored. It's hanging above something else. And if it falls, it has the potential to impact that object and make it move. Does that make sense? That's potential energy, okay? Ball B is sitting on the ground, and it has no potential energy, right? It's sitting on a surface. It can't fall anywhere. It's got no potential energy. Do you see the difference between those two things? Okay. Then if A has released and rolled down this hill, it loses its potential energy as it rolls down the hill. It gains kinetic energy because now it's in motion, right? But it's losing potential energy. So potential energy and kinetic energy are like a sliding scale. If it's got a lot of potential, it's usually got not much kinetic. And then as it slides, right, it loses potential but gains kinetic as it goes down the hill. Does that make sense? Kind of a sliding scale. So A's rolled down the hill, lost its potential energy. It's been lost in terms of friction. It's maybe been lost in terms of heat, right? It loses energy to the surroundings, but it also transfers its energy to B. Okay, so A is going to roll down the hill, hit B, which causes B to move forward, right? And move now up this little mini hill. Does that make sense? What's happening here? Okay, so A's transferred its energy from A to B, and that's what we call doing work. It applied a force which displaced an object a certain distance. That's work. Right? We'll go over that a little bit more in a second. But a lot of words for a pretty basic concept, right? Ball A has energy. It rolls down, transfers its energy to ball B, which now has energy. That's it. Okay? Great. Okay. So continuing with our energy topic, we think of energy most often in terms of heat. Right? We think of energy, and it's really helpful to think of energy in terms of heat for chemical reactions. So heat is the transfer of energy that includes a temperature difference. Right? So if we see a temperature change, that has to be an indicator to us that energy has moved somewhere. Right? There's been some transfer of energy that causes this temperature change. Okay, so although we think of heat as like the only type of energy, it's really not, right? Heat and energy are a couple different things. So we need to understand that heat occurs when a temperature change happens, but energy encompasses heat. Okay? Work is what we talked about a little bit ago. Work is when a force moves an object a certain distance, that means work has been done. Right? Again, that's more of a physics concept, but we talk about it just a little bit here, and so I want you to understand the basics of what that is. You don't need to really get too much into it, but work happens when some force displaces an object. Okay. Last two things, I'm going to give you a second to get them written down, and then we'll talk through that. Okay, the last two things here about being a state function, not a topic that we need to really feel super confident about. Okay, state functions don't really change the way we solve our problems. Okay, but what a state function is a state function means we only care about what's happening in the present. Right? We don't care about how it got here. We don't care about the path it took to get here. Energy is a state function. So that means we only care about what's happening in the present state. So if we look at the energy of a system, of a reaction, we want to know what is it now. Right? We don't care about what happened before. We don't care about how it got there. We want to know what happens now. Work and heat are not state functions. They're what we call path functions, which means we care about how they got there. Right? We care about where the heat transfer was or where the work was done. Again, that's not something that we need to have really, it's not very influential in how we solve our problems. Okay? So yes, it's good to understand what a state function is and a path function, but it's not going to change the way we solve our problems. Okay? Stephen, did you have a question? Sorry. Okay. All right, so let's look a little bit more. We're going to get an equation here for these things pretty soon. When we talk about energy and we talk about a transfer of energy, you need to know two vocabulary terms. These are terms you need to know. System and surroundings. Okay? So the system is what we're looking at. A chemical reaction, right? That's the system. A pot of boiling water, that's the system. Right? Surroundings are everything else. Okay, so you need to know that whatever we're focusing our attention on is called the system, and everything around that is called the surroundings. Those are two vocabulary words that you need to know. We're going to do a couple exercises that help us identify which is system and which is surroundings, okay? So, we're going to do a couple other, we'll get to our examples here in a second. I know there's a lot of vocab kind of to get through. So, endothermic and exothermic are two big ways to describe the energy flow in and out of systems. So, endo, what does that make you think of? Going into, right? Endothermic means heat is flowing into our system. It is absorbing energy from the surroundings. So do you think that means it's getting warmer or colder? It's getting warmer, right? So endothermic means heat is flowing into our system. Exothermic means that it's flowing out of our system. Those are two big terms that you need to know. Okay? And after we get through today, I'm going to give you this kind of sheet I made to help you remember all these different things when they're endothermic, exothermic. So I'm going to give you this cheat sheet. I want you to still have it in your notes, but I'm going to give you a bigger one that kind of puts everything into a picture, okay? So luckily endothermic and exothermic are intuitive terms. So endothermic means into, exothermic means out of. Right? Heat is flowing into or out of our system. Okay, so when water freezes, freezing of water, is it endothermic or exothermic? Don't say anything yet. Just hold on. Think. We'll take a poll here. Endothermic or exothermic? Is heat flowing into our system or out of our system? Okay, how many of you think it is endothermic? How many of you think it's exothermic? Perfect. Okay, can anyone explain why or think about why? It's getting colder. Yeah? Heat's flowing out of the system. And when heat flows out of the system, what happens to individual molecules? That's right, they start moving slower. And when they start moving slower, they start forming bonds that hold them in place, which is called the crystal lattice. Okay? That's why when you see really thin ice, it forms those crystals. That's realistically how those things are bonding together, right? When molecules move slower, they start forming bonds, which causes that solid process. Very good. Exothermic. Okay, we're going to look at each of these, endothermic or exothermic. Okay? Your hand gets cold when you touch ice. So your hand is the system, right? The system is what's underlined. So the ice isn't the system. Your hand is the system. So as I think about my hand getting cold, touching the ice, is it exothermic or endothermic? Exothermic, right? Because heat is flowing from my hand to where? The ice. The ice would be considered part of the surroundings. So the ice would be endothermic, right? But my hand is the system here. So heat is leaving my hand going to that ice. So exo. Okay? Okay. B, the ice gets warmer when you touch it. Oops. What is it? Endo. Okay, right. So that same ice is receiving heat, so heat's flowing in. My bad. Okay, water boils in a kettle being heated on a stove. Endothermic or exothermic? Endothermic. Heat's flowing into the system to cause it to boil. Now, that water vapor has floated into the system and is being condensed on a pipe. What happens? Endo or exothermic? The water itself. Exothermic. It's cooling down. And then ice cream melts. Endothermic or exothermic? Endo, right? It's heating up. Water's flowing into, not water, heat is flowing into the system. Very good. Okay, questions on endothermic, exothermic? Okay, perfect. For each of the following, give a system and the surroundings and the direction of energy. So you need to tell which of them is the system, which is the surroundings, and then is it endothermic or exothermic? Okay, you don't have to write it down. Just think about it. It's okay. You can write it down if you want, but you don't have to. Okay, on A, which is the system? Which is the system for A? Methane is the system, and what's the surroundings? Everything else, right? The lab, whatever. Okay, so this is the system, and this is the surroundings. And which is it, endothermic or exothermic as it burns? As it burns. All right, we don't need that ball. Okay. Here we go. Now we're going to look at energy of our system. The internal energy is the sum of all of our types of energy in our system. Okay, we are going to look at the change in energy of a system using this equation. This is one you need. Okay, I'm going to give that to you on your sheet that I'll give you here in a second, but put it in your notes anyway. Total change in energy. Do you know what this triangle means? This is, yeah, good. It's called delta, and it means change in, or you can think of it as final minus initial. That's what delta means. Final minus initial. So the change in energy equals heat plus work. The heat of our system plus the work of our system. The unit for all three of these variables is a capital J called joules. Joules. Or sometimes it might be KJ, which stands for kilojoules. Right? But joules is the unit for energy. And so you'll see a capital J, or it could be a kilojoules. But joules is our unit for heat and energy and work. I'm going to go ahead and pass this sheet out to you. Actually, I didn't end up putting this equation on the little cheat sheet, so you might want to put that on there if you want to. This is for you just to have a little bit more of a quick reference, because we're going to start talking about what types of things are endothermic and exothermic in terms of work and heat, and sometimes it gets a little confusing. So. You might have to shuffle them around in the back. I don't know if I passed them out. All right, so far on that cheat sheet, all we've talked about is endothermic and exothermic. Okay, you can write this equation on there up to the side if you want. That might be helpful.
The first law of thermodynamics.
You can just listen to this if you want.
The internal energy of a system and the energy flow into and out of the system. This example shows a system where heat enters and work is done by the system. Internal energy remains constant if there is no friction. If instead of adding heat we do work on the system by compressing a piston, then energy will flow out of the system as heat. The internal energy is again constant. Take note of the sign conventions for Q and W. The signs of Q and W are positive when energy enters the system. Here we have a system in which a chemical reaction is taking place. What are the signs on Q and W in this example? Is there a change in internal energy?
Okay, so that video talked about when we have something doing work. They give this example with a reaction that's taking place in a closed container, and if we have something that does work on the system, we have a certain indicator for that in terms of the sign for work. And so I have that on your sheet for you, but I'm going to walk through that here. Okay? First of all, our energy is given in two parts. There's a number and there's a sign for energy. So it always tells us, is heat flowing into the system or out of the system? Okay, so we'll see that with all of our numbers here pretty soon. Okay? If something is endothermic, heat's going into the system, our value for heat, or Q, should be positive, right? That's what, I gave that to you on your sheet, right? If it's a positive heat value, Q, then that means it's endothermic because it's flowing into the system. Does that make sense? Positive heat means it's going in. If you have an exothermic process, then that means Q is negative. It's leaving the system, okay? So that's the value for Q, and I have that on your sheet I gave to you, so you can put it somewhere else if you need, or if you're just going to keep that sheet, that's fine too. Okay? But if it's endothermic, we should have an energy value that's positive, right? Heat's coming in. If it's exothermic, our Q value should be negative, which means we are leaving the system. Okay, so this drawing down here shows us here. If we have an exothermic, that means energy in the form of heat is leaving the system and going to the surroundings. If we have an endothermic process, energy is coming in from the surroundings to the system. Okay, is that all kind of making sense? Even with all the like vocab and stuff I'm saying? Yeah? Okay. Okay, so exothermic means negative work, endothermic means positive work. The equation to solve for work, if it's not given, is this. So work equals P delta V. Okay, and I wrote that on your cheat sheet. Work is equal to P delta V. It's a positive work value if we see a decrease in volume, but if it's an increase in volume, we tack a negative on there. Okay, so I put that on your sheet, and it's here also. Okay, so P is pressure. We're always going to deal with things that are at constant pressure. V is the change in volume. For an expanding gas, we have to change our signs because of it being endothermic and exothermic. We're not going to get into that a whole lot, but I gave you both of those equations down here. Okay, so if the gas is getting smaller, we have positive work. Gas is getting bigger, that means negative work. Okay, and those two things correlate, right? This is just a smaller version of your cheat sheet. Okay, if we have negative work, that means we are increasing our volume, so our system is doing work on the surroundings, and that's exactly what it says up here. System does work on surroundings, negative work, right? Exothermic. So all of these things fit together, okay? They all work together. You need to have this conversion right here. Okay, so you need to say 1 liter times atmospheres equals 101.3 joules. These are conversions between a volume and a pressure unit to get to our energy unit. So you might have to convert that if it's not given to you in the right unit. Believe me, I know all of this seems so abstract right now, but when we start doing problems, I think it will come all together. So I'm sorry that it seems a little abstract and a little out there right now, but we will get there, I promise. Okay, you do need to have that conversion. You can put it on the sheet if you want to. It doesn't matter. I don't. Okay, which of the following performs more work? Which of the following performs more work? So we're going to look at our equation for work, and we're going to decide which of these two scenarios do we see more work happening, okay? A gas expanding against a pressure of 2 atmospheres. ATM is the unit for pressure, okay? So if you see that ATM, it's called atmospheres, okay? So let's look at A, and we'll do the math down here for A. A gas expanding against a pressure of 2 atmospheres and a volume change from 1 liters to 4 liters. So my initial volume is what? 1 liter, and my final volume is 4 liters. Okay, and I'll show you why we need the initial and the final here in just a little bit. When we set up our equation, work equals P delta V, what do we know this delta equals? Change in, or final minus initial. So when we set up our equation, we need to look at our equation for work. And we know our gas is expanding. So what does that mean we need to have? Negative P delta V, right? I said our equation here is for an increase in volume, and is that what's happening here? We have an increase in volume, so we go negative 2 times 4 minus 1 equals work, right? And that gives me 3 times negative 2, which means my work equals negative 6 atmosphere times liters. Okay, work is not in joules in this problem because our units are atmospheres and liter. If we wanted it in joules, we would use that conversion, but we don't have to have that right now.
Wouldn't that be getting less?
This means that work is being done by the system on the surrounding. So it's not that we're losing work, it's just that work is going from the system to the surrounding, so it's flowing out of. That's why it's negative. Does that kind of make sense? Okay, so A we said was -6 atmosphere liters. Does that make sense for everybody? Okay, B, gas is expanding, so we need to use P negative. Oh man, I'm running out of time, sorry. Work equals negative P delta V again because it's an expanding gas. So I say work equals -3 atmospheres times 3 minus 1, right? Final volume and initial volume. So what's that mean? Which one does more work? They did the same amount. So two totally different scenarios, but they did the same amount of work, right? Different pressure conditions, different volume changes, but they did the same amount of work. Oops, sorry, I wrote right where I shouldn't have. Your homework is in your textbook today. Okay? You can put it on the outline. Okay, questions about that one? Okay. Let's see this. Calculate the work associated with the expansion of a gas from 46 liters to 64 liters at a constant volume of 15 atm. We use this version of our equation because we have an increase in volume. Uh-huh.
If it went from like 46 to 40, then you would use the one without the...
Correct. Yes. And sometimes it won't tell you it's expanding or contracting. You just have to know, okay, if my final volume is bigger than my initial, that means it's expanding, so I use my negative. Right? But if it's getting smaller, then you don't. Good question. Okay, so -15 times 64 minus 46. Right? Make sure you do final minus initial. It's really easy to just plug in the numbers as you see them, but you have to go final minus initial.
Why did you get negative?
This was just the negative right there. So 15 is my atmospheres, that's my pressure, and the negative just comes from my equation.
Why'd you move it though? Like the negative.
What do you mean? Negative is just in my equation because I know it's expanding.
You don't have W though?
I just hadn't written it yet, sorry.
Okay.
Work equals,
Um,
I just hadn't written it yet, sorry.
no.
Okay, so 64 minus 46 gives me 18 times -15. So work equals -270 atmosphere liters. Okay, so far our question has not asked us to convert to joules yet, right? It might ask us, what is it in joules? And then we'll do that conversion. But we don't need to just quite yet, okay? How are we feeling about these calculations? Good so far? Okay. All right, you don't have to write these down. We're just going to talk about it just a second, okay? So, an endothermic process that performs work, we want to find the sign of our energy. Are we going to have a positive change in energy or a negative change in energy for these situations? Right? Are we going to have actually, I don't really have time to, I'm not going to worry about this. Okay. We're not going to worry about this right now. You know how to do the calculations. That's fine. Okay, we're going to try some of our problems before because I want to make sure we have time to get the homework going. So, A balloon is being inflated to its full extent by heating the air inside. The volume changes from this to this by the addition of this much heat. Assuming a constant pressure, calculate our change in energy for the whole process. Okay? So get written down what you need to, and then we will walk through this one by one. And I'll get rid of my stuff so you can actually read it. So this joules of heat, what variable does that go with? What variable? It has to be Q, right? Heat is Q. So our Q value is 1.3 times 10 to the 8 joules. It says we're adding this many joules of heat. That is our Q value. So when we go to solve this equation, we have the Q, and we're going to solve for work to get us there. Okay, does that make sense to everybody so far? Or am I going too fast?
Where do you put the volume?
Okay, we're going to solve for work from that equation we've been practicing, and then we're going to be able to plug it in there. Okay, so let's start with that. We're going to solve for work first. Work, are we going to have an expanding gas or a contracting gas? Expanding. So we need to do negative P delta V. Okay? So I'll solve work in a different color here so we don't get confused. I'll do work in a different color. Okay. So work is equal to negative P delta V. So negative 1 times final volume minus initial volume. Okay, so work equals negative 500,000 liter atmospheres. Right? We take this minus this times negative 1. So I got negative 500,000 atmosphere liters or liter atmospheres, however you say it. Yeah?
Is the unit always?
So when we took our pressure, this was measured in atmospheres, and our volumes were measured in liters. So yes, for those problems, yes. But we need it to be in joules in order to go into our energy equation now. So now we need to use that conversion I gave you between liter atmospheres and joules. Okay? So we need to take 500,000 liter atmospheres, and I know that 1 liter atmosphere is equal to 101.3 joules. So I just do a simple T-chart conversion for that. Right? I multiply by 101.3. You could put that in scientific notation if you want. I just went ahead and wrote it out, but you can have it in scientific notation. Negative 5.065 and times 10 to the 1, 2, 3, 4, 5, 6, 7. Okay, does everyone see where that came from and why we did that? If we're going to solve for energy, we need our units for these two variables to match. Right? We can't add something if our units don't match. We can multiply things that don't match, that's fine. We cannot add things that don't match. So we put that into joules.
Of work.
This is work, that's right. So work equals negative 50 million joules, right, roughly. So now I plug that in addition to my heat. So I'm going to do that up here at the top. Okay, so energy, delta energy actually changing, equals 1.3 times 10 to the 8th joules plus negative
Wait, what's the,
joules. Right, because our work is negative. And I get a really big number I'm going to put into scientific notation, so 7.935 times 10 to the 7th joules. I had it as positive because this was times 10 to the 8th minus that number, so I still had it coming out positive.
oh wait, yeah, no, I didn't.
Okay. Okay, does that make sense?
That's what energy.
Our total energy then, 7.935 times 10 to the 7th.
So would you put the delta energy?
Because our initial energy was 0, right? Initially it was 0, and then all this, it changed. So, we see a positive energy value, which means it is endothermic, which should make sense because our heat was flowing into the system, right? Our Q value was positive, which means heat was flowing into the system, so that should make sense to us that our energy came out positive, right? Because our heat flowing in was greater than our work that was being done. So, okay, how do we feel about that?